start that. So again, just a reminder that test 3 is Monday. There's a review in Blackboard. And there's, again, all of the like tutoring stuff is available all week. Office hours, Math Help Center, group tutoring on Thursday. So take advantage of all that stuff. Don't wait till it's too late. The test. So we've done those 3 sections on rational functions. We've got like 2 more to talk about with. We'll start today, but the test is about like 60%. It's a pretty even split between those 2 things. So you've got a good amount of stuff that you can be working on, and also trying to keep up with what we're doing now. Okay, so one thing. I guess I can hand you notes first. So we're going to talk about what we call power functions or root functions. Basically, this is kind of taking a little bit of a sidestep, maybe. Like, we're not really looking at polynomials anymore at the moment. So we'll get into some different stuff in terms of domain and how the things behave and that kind of thing. But we will see, some familiar stuff come up from time to time. Basically, we're looking at more generally, like, what happens if we take a variable, right, x, and throw a power on it that's maybe not necessarily a natural number, like a positive whole number, right? So when we say power function, we mean things that look like y equal x to the b, where this is not necessarily a whole number. If it is a whole number, if it is a positive whole number, then we already know how to deal with it because it's just a polynomial, right? If it was x squared or x to the 5th or something like that, we already know about that. If it's a negative whole number, like, x to the -4, we already know how to deal with that because that's 1 over x to the 4th, right? So really what we're going to be kind of focused on is when that power is a rational number, right? So when it's a fraction. So before we jump too far into like dealing with the functions themselves, I wanted to take a minute and just talk about rational exponents, because that's going to be kind of sitting like underneath a lot of the stuff that we're going to do, is sort of understanding what those mean. So let's just start with something. I'm just going to basically do a bunch of examples, right, of how these things work. Let's say 8 to the 1/3. So first, just right off the bat, we'll take a crack at it. Does anybody know what a 1/3 exponent means?
Like the opposite of something.
Okay, yeah, that's a good way to say it. It's like the opposite of something being cubed. So being cubed means take 3 copies of the thing and multiply them together, right? So the opposite of that, well, what would that look like? Or what do you mean by the opposite of it, Boss?
I guess this one is like, what is the cube root of 8?
Okay, yeah. Cube root. If cubing a thing means take 3 copies of it and multiply them together, the opposite of that, or inverse, basically, is what we're talking about. The way you undo that operation is look for the thing that you would need to multiply 3 copies of together to get this number, right? Well, that's just another word for the root. So, or you could also, if you want, just punch 8 to the 1/3 into your calculator. Put parentheses around the 1/3, probably. But it's the same thing as the cube root of 8, which is 2. This is because 2 times 2 times 2, which is 2 cubed, is 8, right? So that's what that means. In the same way, a square root is a 1/2 power. So like 4 to the, well, let me get away from 2. 9 to the 1/2 is the square root of 9, which is 3, and so on. Okay, so there's that. What if somebody have a calculator handy? What's 8 to the 2/3? Four? Why would 8 to the 2/3 be 4? It is, but why? What's happening there? Yeah, it's the, oh, yes, so it's the cube root of 8, which is 2. It is times 2, but it's times 2 because it's squared, right? So this is an exponent. So basically, for a fractional exponent, right? An exponent that's a rational number, the top is a power like normal, right? So the top is squaring. The denominator there, the third, that's a radical, right? So that's the index of a root. So this is 4 because 4 is the cube root of 8 squared. Cube root of 8 is 2, 2 squared is 4, right? Okay, so just like trying to think through this by hand for just a second. What would 27 to the 4/3 look like? So 27 is we call that the base sometimes, right? The number that has the power on it. 27 is your base. The 4 in the numerator, the top of that fraction is like a normal power, right? So it's like a 4 copies of them multiplied together. The denominator, the 3, that's the index on a radical. So this is 27 to the 4/3 would be the cube root of 27 raised to the 4th. Now you do those things one at a time in either order that you want because they're both multiplication. So what's the cube root of 27? 3, because 3 times 3 times 3 is 27, right? And 3 to the 4th, well, 3, 9, 27, 81, or, just do it in a calculator, right? Like I'm doing arithmetic by hand, like you don't have to, it's fine. So this would be that, right? Now, again, you can do that in either order. I did it this way because I know that 27 is a perfect cube. So I can do that cube root, right? I don't know what 27 to the 4th is off the top of my head. But if you did 27 to the 4th and then took the cube root, it would be a 1, right? So like either order works. And yes, you have a calculator, so like who cares, right? But we're gonna need to like lean on getting from here to here to do stuff with functions, right? So soon it's not gonna be 27 to the 4/3, it's gonna be x to the 4/3. And understanding that that means a 4th power and a cube root is gonna be important in some places. Does that kind of make sense? Okay, so I'm just trying to like motivate it and make sure we understand what the notation means. Let me do one more real quick. How about I don't know. 32 to the 2/5. So what 2 things do we have to do to, evaluate that? What does that 2/5 power mean?
Like the 5 would be the number in front of
The radical or the root?
yeah.
Yeah, so it's a 5th root, right? So the little, that little number there, that's called the index of the root. Your calculator should have a button for it somewhere. I think it's in the math menu. There's like a little like X root thing and you just type in the index. Or you can do it as a raise to the like 1/3 power for the cube root. So that the index of the root, that's how many pieces you're breaking the thing into, right? So this is a 5th root. So what times itself 5 times gives you 32, basically, is what you're looking for in the fifth root. And then the 2 is it's like a normal square, right? So I can either do the fifth root of 32 squared. 32 squared is going to be some big number. A fifth root is going to be a hard thing to do, but like that would be it. Or the fifth root of 32, then squared. Again, if you're doing it, if you're doing the arithmetic and using a calculator, like it doesn't matter, right? Either way is fine. But again, when we get to solving, sometimes thinking about it one way rather than the other is going to be a little more like helpful or show us a little bit more about what's going on. So I just want to, try to really reinforce the idea that like these are the same, right? It's 2 multiplication steps, so it doesn't matter which order you do them in, you get to the same place, right? So either of these is fine. The second one I can do by hand because I know that the fifth root of 32 is 2. So this is 4. And yes, your calculator just spits that back out at you when you type in the original thing. Like I get it, right? Okay, so everybody okay with like how that works? Okay, cool. So we're going to talk about functions involving some kind of power like that, right? And a little bit, I mean, this would include stuff where, if you had a power like x to the 0.1 or something, because that's still a rational number, right? That's the same thing as x to the 1/10. So like that kind of stuff counts as well if it's written as a decimal. Still the same kind of thing. But often, because of the way these things work, there's a way that you can think of it as a root, right? Or something that's got a radical in it. So as just sort of our basic like starting point thing we already know something about that we can use to kind of get into things. Let's think about the square root function. Y equals square root of x. Again, if you wanted to, you could write that as y equals x to the 1/2. We don't, particularly need to do that, right? I'm just, again, trying to like reinforce the exponent thing. What's the domain of a square root function? Looked at that one before. What's it look like? Look what we got. Oh, sorry. What does the square root function look like? It's been a minute, so it's okay if you need to check. See, Jack? It's like half of a sideways parabola that's just sitting in quadrant 1, right? So if you took x squared, flipped it over onto its side, and just cut the bottom half off and just kept the top part of it. So it looks something like that. Well, okay, we can dig into like why it looks something like that, right? Why that's what it does. When you take a square root of something, we've looked at this a little bit, right? We got into the like complex number stuff a couple of weeks ago. When you take the square root of something, what happens? How does that work? If we're talking about functions, if we're talking about graphing stuff, and when we graph stuff in the plane, that's all real numbers, right? Everything there is strictly real numbers. So what kinds of things can you take the square root of? Positive numbers, right? 0 is okay too. But if you take the square root of a negative number, weird stuff happens, right? That's when we get imaginary things coming in. We're talking about domain of a function. We don't care about imaginary numbers at the moment. So strictly non-negative stuff. Okay, well, that's why it starts here at 0 and extends to the right. And when you take the square root of a non-negative number, what kind of thing do you get back? Something that's non-negative, right? Because the square root's, breaking it into equal pieces. That's why it, only goes up, right? Why it only lives in quadrant 1. So what's its domain? How would you write that down? 0 to infinity. And 0 is okay because the square root of 0 is 0. Okay. Well, what's the domain of this thing then? What's different about it? Let's try to look at it in like layers a little bit, right? So like sort of squint at it, right? If you sort of squint at it, the biggest thing there, the like outermost thing that's happening is the square root, right? Okay, so it's going to do square root kind of type things, right? Forget about that, the 3x minus 6 part. It's a square root. Well, how do square roots behave? You can only take the square root of non-negative stuff, right? Positive or 0. And when you do that, you get back non-negative stuff. Okay, so it's the square root of 3x minus 6. Okay, well, I might be able to like break that down and think about transformations and stuff, right? What's that minus 6 going to do? Some kind of shifting thing. The 3, that does a like stretching, shape kind of thing, right? Here's the graph of it. It sits at 2 and goes off to the right. This is because we get into the weird thing where you're like stretching and shifting the same way. And you got to like factor the 3 out kind of, and like stuff gets a little bit weird, right? So it doesn't totally jump out at you that that's going to live at 2, right? Unless you're like thinking about it pretty hard. So like that's what the graph looks like. That's what the function looks like. The domain would be 2 to infinity, right? Another way that we can find that without needing to like just rely on the graph or just like cross our fingers and hope that we can figure out what the transformations are is this idea that if you're taking a square root, the stuff underneath which is called the radicand, the stuff inside the radical, that had better be non-negative, right? Because if it's negative, you have a problem, right? You don't get a real number back, you get something imaginary. So one way that we could answer a question like this is that we need to make sure that this stuff, because it's a square root, right? The stuff inside needs to be non-negative. Right, so it's, kind of philosophically, I guess, it's a little bit like what we did with the rational stuff, right? The rational stuff, we said, okay, well, there's x at the bottom of the thing. That can't be 0 because you can't divide by 0, right? So figure out, what could go wrong and then work around that. We're kind of doing the same thing here. What could go wrong here is if this stuff underneath is negative, because I can't take the square root of a negative number and get something real back. So that's another way I could handle this. I could just take that stuff aside, say 3x minus 6, set it greater than or equal to 0, and then solve. All right, so divide by 3, x is greater than or equal to 2. Okay, well, x greater than or equal to 2 means that the domain is 2 to infinity, which is what we already saw on the graph, right? Okay, so there's kind of 2 basic like pictures that we need to have in mind. One is the square root function. And the other is the cube root function, which we've seen a little bit, but it's, again, been a while. The cube root function, let's take a look at it. X to the 1/3 looks like that. So again, Miles pointed out at the beginning that like a 1/3 power is like the opposite of the cube, right? Well, being the opposite of the cube means that it's the inverse, right? That's what he meant by opposite. which means you take the whole thing and flip it on its side. So this is like x cubed, but flipped over on its side, right? And notice something about this is that because it's a cube, a third root, right? We don't have the same problem with negatives. Because you can take the cube root of a negative number, you just get back a negative answer, right? Because you're breaking it into 3 pieces and negatives cancel in pairs. Agree with me there? Okay, so the domain for this thing would be all real numbers, right? There's no like issue, there's no restriction, there's no place that this stops or starts. It just, keeps on keeping on. So that's the cube root function. This is defined from 0 to infinity. The cube root is defined everywhere. It turns out that it works that way for any kind of even root or any kind of odd root, right? You could kind of use what we know about polynomials to think through that, right? That like x to the 5th looks a lot like x cubed. It's just kind of a little bit like skinnier. The 5th root would look a lot like the cube root, just on its side and kind of like skinnier. So if you have an even root, we have this same kind of thing happening where we got to make sure that the stuff underneath is not negative. If you have an odd root, then kind of anything goes, anything works, right? I can take a cube root of a negative number. I can't take a square root of a negative number. Okay, so here are a couple of examples. So there are 4 there. Think through, and we'll just take 5-10 minutes, something like that. Think through how you would find the domain for each of those, right? So first question is, can anything like go wrong? Is this going to be a thing that's only defined sort of on like a half infinite thing, or is it going to be defined everywhere and then actually do it? Again, main thing to keep in mind is that even roots are going to be sort of restricted like this, where it's just kind of like a half infinite thing because it doesn't exist elsewhere because the stuff underneath would be negative. Odd roots don't have that same problem. And of course, look at the graph and use all that to think through finding the domain. Okay, so real quick, just to kind of make sure we're, on the same page and, being productive. This first one. What kind of a big picture thing is it, right? What kind of function is this? What's the sort of outermost thing happening here? The square root, right? Okay, square root, even root means that this stuff can't be negative. So that's what we need to be looking for, right? Making sure that the thing underneath is, one that's got to be defined, right? But also it can't be negative. Same thing is true on the second one, right? That's a square root. Same thing would be true there. How about the third one? G of X is stuff to the 3/2. What does a 3/2 power mean? It's a square root and it's cubed, right? So I could rewrite that thing if we wanted to as -3 minus x over 2 inside a square root and inside a cube, right? And the cube could be either, of this whole thing like this, or it could be inside, right? Again, just for emphasis, right? Big square root of -3 minus x over 2 cubed. Those are the same thing, right? Because it's multiplication. So does having a cube somewhere, that's x cubed, right? Does that hurt domain stuff? Is there anything there that, that brings into talking about domain? No, it's a polynomial, right? Polynomials are found everywhere. So the x cubed part doesn't really affect it. Neither does dividing by 2 or subtracting or this -3. None of that stuff hurts the domain question at all. The thing that does come into play though is the square root, right? So because of the square root, again, I need to make sure that the stuff underneath is not negative. Okay, what about the last one? What kind of a thing is it? Cube root. Well, cube roots work differently, right? Odd roots are different than even roots. Cube root looks like that, right? It's defined everywhere. Because breaking a thing up into an odd number of pieces is different than breaking it up into an even number of pieces, right? Because odds cancel in pairs, so you can have one left over. So negatives are okay now, right? So as long as that thing underneath like is defined, as long as it exists, 8 minus 2x, as long as that's a number, a real number, then you're good to go here, right? So I don't have nearly as many worries about that one. 8 minus 2x, there's nothing weird that's going to go on there. When I say like nothing weird's going to happen, I mean like if that was say it was the cube root of like 1 over x, like x still can't be 0 because that would be undefined, right? But other than that, everything's fine. Like nothing else is going to sort of break that. So that last one, the domain would be the whole real line, right? That's defined everywhere. Okay, and let's, I don't know, talk about one of the other ones. And any one of those look more interesting than the others? This one maybe. So that stuff can't be negative, right? So I need to make sure that 3 minus x is greater than or equal to 0, right? Solving that, we could subtract 3 from both sides and then divide by a negative, but be careful when you divide by a negative because that's an opposite. The inequality flips as well. So the domain there would be all x values less than or equal to 3. How do you write that? And also look at the graph along with it if you want. It's still got the shape of a square root function, but it's facing the other way, right? Because that minus x in there, that's a reflection, right? That flips it around. So the domain should be everything from negative infinity up to 3, and then it sort of cuts out there. Okay, and the other two, just so you have answers, that's -3/5, that's -6. As you have, once you've had time to like look at all of them, if you have questions about anything, something else. But so the first big, like think about it like a decision tree flowchart kind of thing. If there's a root in there or a power that you could think of as a power that means a root, right, like this, then is that root even or odd? If it's even, you got to make sure stuff underneath's not negative. If it's odd, then you don't have to worry about that, right? Which is why I made a big deal earlier about thinking through what that power means. Okay, so that's pretty much how rational exponents affect dealing with like a function, right? So if there's a root in a function somewhere, the main thing that we're going to be kind of concerned with is figuring out where it actually exists, where it's defined. So it's a domain question, because that's going to affect stuff like solving equations as well. So just real quick as kind of a starter for tomorrow, and then we'll do some more of this, but how would you solve something like that? Okay. Why do you want to square both sides, Emily? Yeah, because that's the opposite of a square root, right? Squaring the square root is going to get rid of that. So you get x is 4 squared. 4 squared is 16. And we can check, right? Square root of 16 is 4. Okay, cool. Looks good, right? That's the basic idea, right? If we can get there are a couple of things that are going to come up that we need to be careful about, of course, but if we can get the root by itself like that, like this one is, then if I do the opposite thing, right, apply the opposite power to both sides, then we should be good to go. So how would this work if I was trying to solve something like square root of x plus 1 equals 4? Well, what's the biggest thing on the, I still can't do left and right. On the left-hand side of this thing, what's the sort of biggest thing that's going on? The square root, right? It's all by itself, right? I've got the square root of the thing. So as we've, done sometimes before, don't worry about that yet. We'll get there. But first we got to peel away the outer layer, right? Which is the square root. It's all by itself on that side of the equation. So if I do the opposite thing to it, and if I do it there, I got to do it to both sides, then the square root goes away, right? That cancels the root out. So on the left, we get this equals 4 squared, which is 16. And the only difference here from the one that we just did is that we're not quite done yet, right? So what do I still need to do? Subtract the 1. So x is 15. You take 15, you add 1 to it, and then you take the square root and you get 4, right? Okay, one more real quick. What if all that same stuff, but it was the square root of x plus 1 minus 1 equals 3? Again, we're trying to solve, right? So we're trying to peel away the layers to get to the chewy nougat inside, which is x, right? So what needs to happen first? Add 1 to the other side, right? Why do we want to add 1 to the other side first? Yeah, to get rid of it, to get the square root by itself, because the minus 1 is the last thing that would happen here, right? And when we're solving, we're always kind of, working backwards, right? We're trying to take things away one at a time, but you want to get rid of the last thing first. So this would be sort of the outermost thing that's happening, right? It's the subtraction. So deal with that first. Also, if you square that as it is now, it doesn't do what you want it to do, right? Because if you square that as it is now, you have something like that. How do you multiply that out? This is 2 things. This is 2 things. So you would FOIL, right? Which means you multiply those, but then you get this messy minus 2 square root x plus 1 term, and it doesn't do what you want it to, right? It doesn't cancel the radical. This would be x plus 1 minus 2 square roots of x plus 1 plus 1, in case you're wondering, which is worse, right? We went the wrong way. I'm going to say this, and somebody's going to do it on the test anyway, but that doesn't that doesn't work, right? The only time that squaring is going to cancel the root out the way you want it to is if you have the root all by itself first. So first thing here would be add 1. Then we can square. And I mean, we've already done this, but subtract the 1, 15. We've seen this other places where the first thing we want to do to solve is, isolate and then start working on undoing, right? So this is me isolating, getting the root by itself. Then I'm going to start undoing it by doing the opposite thing. If it was a cube root, then instead of squaring, I would cube both sides, right? Because that's the opposite for a cube root. Okay, so I'll we'll leave that there for right now, and we'll pick up there tomorrow. There are some tomorrow we're basically just going to work a bunch of problems with equations, but I do have one tiny little baby quiz problem for you that we'll spend the rest of class on today. So hang on the notes. We'll pick up there tomorrow, but put them away for now. One, hopefully straightforward enough. It's a rational equation to solve. Calculated stuff if you want one, or else then you read it, but